Hello and thank you for joining us all today. We are going to start the meeting now. I must mention a few special people who are here with us today. Special thanks to our principal, Dr. Shormila Mitro, who is the principal of Behala College. Thank you, ma'am, for being with us. And special thanks to our convener, Dr. Pratap Kumar Shaha, who is now going to give the welcome speech. Dr. Shaha, the mic is yours.
Yes. Respected Principal Madam, Dr. Shormila Mitro, Honorable Chairperson, distinguished speakers, and in the audience, respected teachers and beloved students from different colleges and universities. I, Dr. Pratap Kumar Shaha, as convener of this webinar, welcome you all and convey my greetings to everyone at the very beginning of the today's webinar at national level on pure and applied mathematics. We are fortunate to host some of the finest professors amidst their busy schedule in our little endeavor. We are in debt to them for their support and looking forward to get inspired by their wisdom. We also wish that the students who will be hearing the speeches delivered by different speakers will be enriched through spending some moments in this webinar. So I will not take time further. Let us start the webinar. Hope all of you will enjoy. I hand over the microphone to our chief patron, our principal, Professor Dr. Shormila Mitro, to hear some valuable talks. Please, madam.
Good evening. Good evening, everybody. On behalf of Behala College and Mathematics Department, I welcome all participants for participating this 2 days national webinar on pure and applied mathematics. I welcome our president, Dr. Aurobindo Ghosh, for his active motivation. Welcome. I welcome all my governing body members for the same. I welcome all my honorable speakers. It is my pleasure to assemble the galaxy of stars here in Behala College to this webinar. Namely, Dr. Roger Shubro Hajra of ISI Kolkata, Dr. Ritobroto Uchi, ISI Kolkata, Dr. Muhammad Ali Jinnah, ISI Kolkata, Dr. Proshenjit Rai, IIT Kanpur, Dr. Somnath Jha, IIT Kanpur, for sharing their valuable time and knowledge with us for these 2 days. Established in 1963, Behala College has a long, glorious past history. At present, we have 21 departments and 4 PG departments, of which mathematics is worth mentioning. I really feel proud to say that we are running this department glamorously, and I'm grateful to renowned mathematicians, our visiting faculties like Dr. D.K. Ganguly, Professor S.K. Acharya, Dr. T.K. Dotto, Dr. Falguni Mukherjee, and Dr. U. Utshab Chaudhary. Am I audible? Can everyone hear me?
We can hear you.
Okay. Behala College is graded A by NAC and undoubtedly have achieved a great in academic score amongst all the renowned colleges under Calcutta University. As we all are aware that the whole world is passing through a pandemic beyond expectation, which has disturbed not only the financial condition, but in the field of education, we find that there is a stagnant situation. But at the same time, this pandemic has a positive side also. It has opened the window of technology, and a wide range of online programs are coming up, which is undoubtedly a very positive side. But I feel proud to say that Behala College has taken this step long back 5 years ago. And we have already developed our own platform, and we have upgraded technological systems whereby we are running stakeholders. We have online profile mapping for students.
Madam,
We
I'm
have
sorry to
online
intervene for
360-degree
1 second.
evaluation for
Dr.
faculty
Sharmila Mitra.
members. Yes.
Hello,
Yes.
I'm sorry for intervening. I'm just going to make one small announcement.
Okay.
Rakhi Bera, please turn off your microphone. Members of the audience will always have to keep their mic and video off throughout the duration of the seminar. Otherwise, it is causing a big disturbance. Rakhi Bera, please turn off your microphone. Everybody, please turn off your microphone and video except the speaker. Thank you. Madam, you can continue. Sorry for the disturbance.
As I was saying, that 5 years back, Behala College has developed its own platform of all these online facilities. We have an online feedback system for students and stakeholders. We have an online e-diary, daily diary work distribution program. We have profile mapping for students. We have profile mapping for students to make and to understand their level of knowledge. We have online classes for placement of students after their graduation, because our goal is not only giving them education, but from learning to earning. So in this way, Behala College is progressing a lot. our future plan is to enrich the students with all types of facilities and support so that they can make a place wherever they go and whatever they feel. In this regard, I would be proud to declare and say that we depend on this department, mathematics department, and our goal is to make it a research-oriented department in the near future. I welcome once again to all the members who have worked hard all these days to make this webinar successful, especially the organizing committee and convener of this webinar. I thanks a lot to Right Brains Technology who have given this technological support to make this webinar successful. I really thank my faculty members of this department who have taken the initiative to hold this webinar. And last but not the least, all my support staff of Behala College who all are working hard to make webinars of all departments to a great grand success. Please stay safe and sound. May God bless all of us. Thank you. Thank you so much.
Thank you, Dr. Mitra, for your talk. And now I must announce that we are going to start the technical session 1, under which we have with us two eminent speakers. First, we have Professor Rajat Shubhra Hajra from ISI Kolkata, who will give a talk on probabilistic aspects of complex networks. Next, we have with us Professor Ritobroto Munshi from ISI Kolkata, who will give a talk on transcendental number theory. The chairperson for us today will be the eminent Professor Dilip Kumar Ganguly, who is the Vice President of Calcutta Mathematical Society and a retired ex-professor of Calcutta University. We are going to give a small break of say 1 or 2 minutes so that Dr. Hajra can arrange the material and the files for the presentation, and we will begin shortly. Please do not leave the meeting. Please keep your mics muted and your video off, and we will begin shortly. I now pass on the mic to Dr. Professor Dilip Kumar Ganguly, who will now take over the role as chairperson. Dr. Ganguly, the mic is yours.
Yeah, thanks to the organizing committee. So in this session, technical session 1, we have two speakers. One, Rajat Shubhra Hajra. He at present, Rajat Shubhra Hajra is in the StatMath division of ISI Kolkata. He passed MSc from the Department of Pure Mathematics from my department. Then he did PhD in ISI Calcutta. And as far as I know, Rajat went to Zurich, Switzerland, at the continue some work at ETH. I remember so. Is it so, Rajat?
Yes, sir.
Right?
Yes, sir.
So I request Rajat. Rajat, you are ready?
Yeah, I'm ready. I'm ready.
Okay, I will start.
Yeah, definitely.
Okay. Now, Rajat, I request Rajat to deliver his lecture, but your time is allotted for 1 hour. After
Thank
that,
you.
there is a question answer session during the 15 minutes. Okay, Rajat, go ahead.
Okay. Indranil, can I share my slides now?
Dr. Hajra, you can.
Okay. So just before sharing, Indranil, if there are too many, I won't be able to see the chat during the presentation. So if there are too many questions, feel free to stop me. And also, if I'm going over time, then also please stop me, because I might not be able to see the complete time in that.
Yes,
And I
yes,
request,
Professor, that's not a problem. The questions will be typed only in the chat box, and we have been instructing the students to type the questions only at the starting of the question and answer session, so that it doesn't disturb your lecture. Our chairperson, Dr. Ganguly, will pick up the important questions for you to answer.
thank you. So yeah, let me begin by thanking Behala College principal, and especially Pratap, for arranging everything and this talk, and everyone who is listening to this talk. Uh, uh, I'm trying to now go into the full screen mode. Uh, so since there is a lot of audience today, so what I decided would be, I'll be speaking on something which is broadly general for everyone, so that it's a bit easier to understand what is going on, more pictures and less technical stuff. So always feel free to type in your questions in the chat, and please kindly remember to mute your microphones, otherwise there will be an echo, and also we can hear things going on at your home which are kind of embarrassing. So please try to mute your microphone just for your own safety, I guess. And uh, so here is the title of my talk. The talk is split up into a few parts. So first I'll show you some pictures about how networks look like. That will be under the heading of network modeling. And we'll also see what kind of features does a complex network has. And then we'll be talking about one of the simplest complex networks, which is the Erdős-Srény random graph. And then I'll show you something about what is this is a more modern approach to random graphs and complex network, which is called the configuration model. And then we'll show the importance of trees everywhere. So if, okay, that time permits, we'll see that part. So here is broadly the aim of the talk. So the aim of the talk is to find geometric properties of very large graphs. And large graphs, I mean large graphs which are more aligned to real life networks. Now, what kind of networks do we see nowadays? Nowadays, as everybody was pointing out, especially like our life is now going completely online. So first of all, the most important network we see and use every day is Facebook, Twitter, Instagram. Even big leaders, everybody uses the Twitter nowadays. Every announcement is done in Twitters, and Facebook. People are always posting things, sharing things. We find old friends. So it's a huge network. I'll show you some pictures, some typical pictures from the Facebook website or these things. Then there is another important network which has been long time with us. It is the banking network. So there can be networks where the banks transactions within the banks. So for example, you have SBI, and there are branches of SBI which are making transactions with themselves. So there can be networking between them. There can be intra networking, where you are talking about, okay, intra is the internal banking, and inter is, say, SBI is working with, say, Allahabad Bank or something like that. Then there are loan schemes. The third point is the most important point, because nowadays, due to Corona, we keep on staring at graphs, we keep on staring at numbers, we keep on looking for different kind of things which are happening. And biological networks, especially epidemics on network, is becoming one of the biggest things, at least for 2020. So everybody is bothered about it, and we'll show some of the pictures. And then there is a collaboration network. So if there are two actors, they act on the same movie, then we say they are collaborating. If there is a paper we are writing, research paper, and if we are citing another paper, then that means that the papers are kind of having a citation network. That's the citation network. And there are collaboration networks also. So there are many kind of networks we face in everyday life. and let us see some pictures. So first, let us start with something which you are encountering every day. This picture is not visible properly, but those who can see it, it's a sequence of alphabets. So it's like A U G U U U U G U. So this is what does like this is a RNA of a coronavirus looks like, and you can't make much out of it. So what one does is this is split into small parts. For example, codons. See, these codons are named after, say, has 3 alphabets in it. It can be AUG, UGC, like that. And there is an interaction which is happening here, and you get a sequence of which is formed in this. So if we split those codons, and so here you see a network visualization of the coronavirus spike in RNA proton. So each of these big dots are called these are the nodes. So these are small parts.
Hello, Dr. Hajra, can you hear me? Professor Hajra, are you with us? We seem to be facing some technical issues. Please be patient with us. Do not leave the meeting. We will resume shortly. Dr. Hajra, are you with us?
Indolin. Hello, Indolin.
Yes, sir.
You make a phone to Hazra whether there is any problem. I think some network problem. Have you any phone number to Hazra?
I'm contacting him. Please wait. I'm contacting him. Members of the audience, please do not leave the meeting. Please be patient with us. The meeting will resume shortly. Dr. Hajra is being contacted. Please stay with us. Be patient with us. The meeting will resume shortly.
दोबारा तारीख नয় তাহলে ওটা দে
Dr. Hajra is facing some technical issues from his side. He is restarting the application and joining the meeting. It will take a few minutes from his side. So I request all of you to please stay in the meeting. Do not leave the meeting. The meeting will resume shortly.
দেখা হয়ে গেছে এই তো অলরেডি রেসপন্স লেখা আছে
Rakhi Bera, please turn off your microphone. I repeat, Rakhi Bera, please turn off your microphone. The microphone is to remain off for all audience members throughout the meeting. I repeat, Rakhi Bera, please turn off your microphone. Thank you for your cooperation. Professor Hajra is restarting the program and joining the meeting shortly. Please stay with us. Do not leave the meeting. Thank you. Professor Hajra, we cannot hear you. Professor Hajra, we cannot hear you. Professor Hajra, we still cannot hear you. Yes, we can hear you now. Professor Hajra, we've lost you again. We cannot hear your audio. Professor Hajra, we cannot hear you. Your audio is not coming to us. Supravat Sarkar, please turn off your video. Supravat Sarkar, please turn off your video.
Hello, hello.
Yes, Professor Hajra, we can hear you now.
Okay, good, good. Sorry about this. Sorry about the. As you can see, online things. Whatever you plan is not in your hands. I'm sorry. Thank you for waiting. Those who are waiting still. Uh, uh, my computer completely crashed suddenly. So and yeah. Anyway, let's go on. Whatever time remains, I'll not take an extra time. Thank you for waiting. So this is so just I wanted to show you that this is a corona spike protein, uh, and you can see how complex structure there are. So each of these nodes, as you can see, all these nodes are, for example, all these small dots are these codons which are there, and there is an interaction between these codons. And whenever there is an interaction between the codons, you find that there is an edge between them, and you can see that multiple codons can link with multiple codons. So there is a very, very complex structure which is happening in this coronavirus protein. Now, what we want to know is, how does this actually topologically look like? We don't have a concrete answer for it, but let us look into some similar kind of graphs which we can see. For example, this is a networking graph from the Brazil interbank network. So this is so as you can see, all these red dots are banks. All these red dots are banks, and whenever there is a transaction between two banks, there is an edge between them. So it is also, as you can see, it's a very, very complex structure, just as the coronavirus graph. Now this is another, it's a pictorial, it's taken from the Facebook. As you can see, what we have is, in Facebook, you can think of all these users as the vertices, and whenever you are friend with someone, that someone is also a friend with you, so you have a edge between them. And this is a sort of very artistic diagrammatic picture of a Facebook network, which is a huge network. As you can see, there are almost in India and Brazil, we have the maximum users, and it's a very, very big network we have. Another network which is becoming very popular, which has become very popular, is the Twitter network. Here, what are the nodes of the graph? The nodes are the users, and whenever someone retweets or someone follows someone, then you form an edge, and it's a directed edge. In Twitter network, it's a directed graph, in the sense that, say for example, I may follow Amitabh Bachchan, but Amitabh Bachchan need not follow me. So there is always this is a directed graph in that sense. Then this is a similar kind of complex network, which is now known in a very big detail. This is the HIV protein network. It acts just similar to the coronavirus, and this is a beautiful diagrammatic representation and of the interaction between the proteins or the RNA structure of these HIV protein thing. It's quite similar to what we saw in the coronavirus. It's just pictorially presented in a nice way. This is an interesting network. I didn't find an Indian one, so I'm taking it from the Hollywood. So this is called the Movie Actor Collaboration Network. So if there are two actors who have acted together, then they form an edge between them. So here, as you can see in this graph, there are big dots. What does this big dots mean? Say, for example, Leonardo DiCaprio, Tom Hanks, Robert De Niro, Brad Pitt. These are all big dots in the sense that they are connecting many small dots, and these big dots have done movies with many people. So in the sense that it's not that they have done lots of movies, but if you randomly choose one actor and say that has he acted in that movie, yes, you'll find that okay, he has acted in a Tom Hanks movie or a Leonardo DiCaprio movie. It might be very short role, but these are all famous actors. So that's why in graph theoretic terms, what does this mean? We'll come to it later also. This means these vertices have huge degrees. So they have lots of edges coming out of them. So in a graph, we would like to find out what are these big superstars are, what are these vertices are which are very, very big. Similarly, this is something which interests the mathematicians. Paul Erdős was a famous mathematician who used to roam about with a suitcase, and he used to collaborate wherever he used to go. He used to collaborate with people. And this is a collaboration network of Paul Erdős. So vertices are here mathematicians, different mathematicians, and this is whenever Paul Erdős used to write a paper, you can form an edge. And this is famously now known as, so we count this as the Erdős number. For example, my Erdős number is 3. So in that sense, so I need 3 vertices to go to Paul Erdős. So how does it go? So I have written a paper, say, with my colleague, Professor Arup Bose. Professor Arup Bose has written a paper with Professor Gutti Jogesh Babu, and Gutti Jogesh Babu has, Professor Gutti Jogesh Babu has written a paper with Paul Erdős. So exactly, so my Erdős number in that case becomes 3. There are many people who are like having Erdős number 1, Erdős number 2. So this is, so what does Erdős number 3 mean? So I am at a distance 3 in the graph from Paul Erdős. So this is a very, very complex network, and this is very interesting for mathematicians because you see how many papers or how big or complex network Paul Erdős is formed. Now, I'm showing you some certain webs. So you can form many other things. For example, the whole internet, www, the World Wide Web. It's a big complex network. It's one of the biggest one, and it's extremely huge. Now, all these pictures, we want to make a meaning out of it. So what are the things, or we want to model these things? These are some things which occur naturally. So we want to model these things. So how does one model these things? So first basic thing, what one does is, say, suppose, Indranil, is my cursor visible, sort of? This plus sign, is it visible?
Yes, your cursor is visible.
Okay. So you can see points X and Y in RD. So these are all points, say, in RD. You can think of it as a plane. Say they are points in the plane. Now what you do is, what you will need is, for every point X and Y, you will need a number which we call the probability, Pxy. So this might depend on X and Y. This may not depend on X and Y. So what does this mean? That X, this is with probability, Pxy, X and Y is connected. So you are like assigning a value which is called a chance of having an edge between X and Y. Say for example, it might happen that I am friend with Amitabh Bachchan, but you are not. But still in the graph, you are 2 points. Say you and Amitabh Bachchan are 2 points. So we want to assign a probability, say probability 0.0001, that there is an edge between you and Amitabh Bachchan. So this is a collection of probabilities we want to give. It might be very small. it might be very big in that sense. So this is a basic idea about constructing random graphs. Now, what happens if pxy is small? If pxy is small, what does this mean? That chance of having an edge between x and y is very small. So when you look at a graph, you'll have less number of edges. If pxy is small for all xy, for example, the graph on this side, this has very few edges. And on the right hand side of your computer or laptop or phone, you can see that there is a graph where pxy is larger. So that means there are lots of edges in them. So this is a more dense like graph. For example, we saw a connection or a network of the coronavirus where pxy was very large. Now, coming to some notions in networks which will be necessary for talking about the mathematics, but these are very simple notions. I won't get into the technical notions. Degree is something which we know, everybody knows, but let's remind us. So when we say degree dx, we mean that if we look at x, we count the number of edges of x. So dx is just the neighbors. We are counting how many neighbors or how many points which share a direct edge with x. Now, as we go back to if you recall this picture, if you look at the degree of Leonardo DiCaprio, it's very high because there are lots of edges going there. So that means these nodes with higher degree indicate that these are hubs in the network. So these are big points in the network. That's what we call the hubs. Now note that what we are saying, that there is a chance that x and y are connected. It might not be connected, it might not be connected, so there might not be anything. So since there is a chance factor, in probabilistic term, we call this random. And if there is a chance of edge happening, we can see that dx can be random too. So this is what is called a random variable in mathematical terms. So it's counting the number of edges out of x, but since you don't know precisely whether there is an edge between x and y, so this is a random quantity. Now this is a picture which I was saying that there is a red dot here or blue dot where lots of red rays are coming out. These are the hubs. So there are lots of edges, and there is a green dot, small green dot, which is not possibly visible in many computers. So there is a small green dot which has very few edges which are coming out. Now there is another notion which will be important again. This is called a graph distance. Suppose you have a graph here which is in the gray points. Now we say the graph distance dxy, say I am at this point, I want to go to that point. Dxy is the minimum number of edges that is needed to go from x to y. Say for example, if I want to go from Behala to Bonhugli, I can go via even Damdam, I can go via directly Shambazar, but I want to know the shortest route that is possible, and that will give me the dxy in the graph. So dxy, remember, is the minimum number of edges that links the particle x to y. Now, what is a connected component of a graph? The connected component, which we denoted by, say, I take a point x. Cx means that I look at all the y's I can reach from x. It need not be a direct edge. I can just make a path which is going there. Say for example, this is my graph on the left hand side, and I'm looking at a connected component of this graph. As you can see, it's a huge graph. All the red parts are a cluster of each of these points. So mathematically, again, what is Cx? Cx are all the points which can be reached from x to y. So this is a collection of all y's where y and x are connected by a finite path. So if you are not connected, if a point is isolated in the sense that you cannot reach that point, then it's not in the cluster. So these are all possible points. When you start from a point, you can reach the other point. So this is called a cluster. And this is also called the connected component of the graph. So what kind of questions do we ask in such a models? That's the first important thing. So you have to ask the right questions to answer this. Now, as we saw, there are many networks. So what are the questions? The questions would be, what kind of connection probabilities PXY should one choose? How to model a random graph which is matching with the pictures we saw. So how does this graph look like? This is a very important question. We'll see that. How does this graph look like if I have huge number of vertices? What is the size of the largest cluster? For example, now in the coronavirus, it's a very, very important thing, which is we are now knowing these terms, that contact tracing and all these things. So this is a very, very important question, that how big a cluster is in the graph. Then we'll talk about whether there is a phase transition in the graph behavior. So in the sense that whether there is a parameter with which we can change the picture in the graph. And this is called, in the physics literature, this is known as the phase transition. We'll see one such phase transition today. And this is, last part will not go there. One of the important properties is to understand what is, so suppose I have a graph. We want to study spread of infections on this graph. For example, spread of infection on a human being, fake news, rumors, and we want to find out, for example, in the fake news case, fake news is very important these days. We know that people are getting all these messages from WhatsApp University, and people get angry reading some news. So one needs to know, when a fake news spreads, how large is the radius on which the fake news is spreading. So this is very, very important, that we need to know how big the fake news world is. Now here is one picture or three pictures of how a large graph looks like. So here is a picture of how a large graph looks like. Now this is almost a picture of the network I showed you, except that I have removed the multiple edges which are there and any loops. So this is looking like a tree. Essentially all these graphs look like a tree or a forest. You can think forest in a technical term is a collection of trees. This is another graph which is a bit more bushy, I would say, in the tree sense. This is a third graph. I wanted to keep this. I'm sure that very few people might be able to guess what graph this is. This is a simulation of something very interesting, not related to graphs, but this arises naturally. This is a picture of what is called a quantum gravity. So as you can see, all these pictures, a network, a complex network, and quantum gravity, all have certain things which are very, very similar, and these are very naturally made. This is not we are creating it. This is nature is creating these things, and we want to understand what exactly are these. So now to understand what are the features. So all these features you saw, we want to know. So there are hundreds of features of a Facebook network or any social network. Now, what are the features we want to take from there so that we can use it for mathematical modeling? So here comes the first interesting feature, which is called the 6 degrees of freedom. Now, 6 degrees of freedom was a term which was coined by John Guerra, or it was there, but John Guerra made a play in 1990s, and this notion came in, and later in 1993, that play was also translated into a movie by Will Smith, which is also called the 6 degrees of freedom. There is a quotation in this movie or the play which is very important, and which has become the basis of today's study. So let me read the quote for you slowly. I read somewhere that everybody on this planet is separated by only 6 other people. 6 degrees of separation between us and everyone else on this planet. The President of the United States, a gondolier in Venice, just fill in the names. I find it extremely comforting that we are so close. B, like Chinese water torture, that we are so close because you have to find the right 6 people to make the right connection. I'm bound to everyone on this planet by a trail of 6 people. Now, this was 1990. Remember, 1990, there was no Facebook. There was no Orkut even. So people still believed that anyone, for example, I am connected to the President of United States by 6 degrees. So that means if I choose 6 correct vertices, I can reach somehow in a network the President of the United States. Now, this has been reduced now. So this is what Facebook writes. Facebook writes, each person in the world, at least among 1.59 billion people active on Facebook, is connected to every other person by an average of 3.5 other people. So as you can see, so Mark Zuckerberg, this is the picture on the right, who is the founder of the Facebook, has 3.17. And another, Sheryl Sandberg, she is the CEO of Facebook, and I think now the managing director. She has 2.92, which is perhaps reducing also now. So in a sense, what does this 2.92 and 3.17 mean? It means that if you pick any people and Mark Zuckerberg, then you can reach that any person can reach Mark Zuckerberg through 3 other person, in the sense that, say you pick me, I'm friends with let's say Saurav Ganguly. Saurav Ganguly is friends with say Narendra Modi is friends with Mark Zuckerberg. So it's just 2 in that sense. So at an average, so this is an average number. You can't say that, okay, I don't have a friend, I have just 20 friends in Facebook, so I don't have this number. But still, okay, it's an average out of a billion people. So that's why this number comes. Now, this is my time for 6 degrees of freedom. Since we are bit in a relaxed mood, let me tell you a small story. So so this was a few years back, in 2017, December, I gave a martingale theory question paper where there was a question about, okay, Mr. Trump, Mr. Trump. And it was just, the question was very simple, that out of English alphabet, if Mr. Trump types something, then what is the probability that he will type the word Kopfefe? So it's a nice martingale theory problem. The answer is very simple also, and one can forget it. Now, after the exam, I went back. Next morning, I got a call from the director of the institute. And I went there. The director said, the Ministry of Home Affairs has called, and there is a query from US saying that I have posted a question on Mr. Trump. So as you can see, so then I realized what's happening. I went to Twitter, I went to Facebook, and I saw that this is trending as number 3 in Twitter, and everybody is tweeting it. And it has somehow been tagged to Trump. So in that sense, even if I am not in in Twitter, I got tagged in a 6 degree of separation with the president. Okay, nothing happened to me. I'm not in jail or anything. I'm still fine. It was just a nice question. So this was 6 degrees of freedom. That means if you have to construct a graph, your graph should have a property that if you pick any 2 person, they will be really, really close in your graph. Now, how to pick that up? So we'll see how to pick that up. Another thing is, this we won't be talking about in this talk, is a clustering property. Clustering property means that the connected particles, whenever there is a connection, the connected particles tend to share common friends, in the sense that you can see here this picture that of India. India Facebook is connected almost there is a huge cluster of people which are connected together. Similarly, in this part of US and in Brazil, and also in some parts of Europe, there is a huge trend for these things. Now that means that friends tend to cluster together. For example, you are going to, for example, if somebody from Behala College is a friend, then he will be friend with most of his classmates in his Facebook. So that's forming a cluster. So those are the clusters which are formed. Another is very, very important. This is called a scale-free property or a power law property of this graph. So if we look at the degree distribution of a particle, so in the sense that the number of connections, say a particle X has. So what are the chances? So here I'm looking at the probability, or what are the chances that the degree is K. We need the networks to have it proportional to K power minus tau. So the chance reduces as K increases. So the number of vertex, so huge number of vertex having a particle, each particle having huge number of vertices is really low. It's not zero, it's low. So these are some empirical evidences that things look like. For example, number of oriented links on web pages where tau is 2.5, then routers for emails, the tau is 2.2, movie actor network, this is calculated in 2.3, citation networks is 2.9. So everywhere you see this tau, this is a naturally occurring phenomena, all these four. And it's predicted that the tau is between 2 and 3. Okay, so these are three properties I said. So let's remember these three properties. This is one is that 6 degrees of separation. Another is clustering property. Another, the degree distribution is very, very small with high with very, very small probability. So it has a power law. So this is called, since this is K power minus tau, we call the degree has a power law. Now let us come to, let me, I don't know if possible to see the chat at this moment, but maybe I'll go later. Uh, uh, Maybe I'll take the questions later in 15-20 minutes. So let me go to the simplest of the graphs. So this was introduced by two Hungarian mathematicians, Paul Erdős and Alfred Renyi. Both are big mathematicians, have made huge contributions. In 1957-58, they wrote a very interesting combinatorics paper, and that paper introduced this graph called the Erdős-Renyi random graph. So how does this go? Let me construct you the graph. So what you have is you have n vertices, which I call Vn. Choose a p between 0 and 1. Now take any pair of vertices I and j from Vn. You toss a coin. You just throw in a coin. If it's head, you put an edge. If it's tail, you don't put an edge. Again, I'm repeating. You take two vertices I and j, toss a coin, and if it's head, you put an edge. If it's tail, you don't put an edge. And suppose the chance of falling head is p, and the chance of falling tail is 1 minus p. So for example, p can be half, so equally likely. So our coin can be equally likely. So, and you do this independently in the sense that if you're doing it for say 1 and 2, and if you do it for 2 and 3, it should not depend on each other. You do it independently of all the ordered pairs. So you must take a fair coin in the sense that it should land on head and tail, and not like Cholet, it lands in the middle also, and or has tails on both sides. So it's a fair coin. You toss a coin, and so for example, these two, if you look at this graph, if you say this, if you look at this edge and this vertex and this vertex, there is no edge. That means it has fallen a tail, and there is an edge between this. So let me, I don't know if this will be visible. Maybe is this visible? Anyone tell
Yes,
me?
Dr. Hazra, it is visible.
Okay, so here I am showing you a simulation of a Erdős-Renyi random graph. I'll say what lambda is. Let me choose this lambda to be, so p I am choosing to be lambda by n. Lambda is 0.5 and my n is 30, and p is just lambda by n. So this is what is happening. So you can see for each of these edges, what you have is there is a graph which is being formed. Now this is very low, so let me increase it to 1. Okay, so this is a graph. As you can see, this is an Erdős-Rényi graph. For each of the pairs, the computer has tossed a coin. Whenever there is an head, it has given an edge. Whenever there is a tail, it has left it without an edge. Okay, so now what are the basic properties? For example, the degrees, if you calculate, say the chance of having the dx having a degree k is given by, so I'm looking at, so what does degree dx is equal to k mean? It means that if I look at the vertex x, it has k edges. Now, what does this mean? Whenever there are k edges, there are n minus 1 minus k non-edges. Now, what is the probability that there will be k edges? So that means you have heads k times. So that's why there is a p power k. And you have tails n minus 1 minus k times. That means we have 1 minus p to the power minus k. And what you're doing is, if you leave out the vertex x, you have n minus 1 many other vertexes with which it can join. So you have n minus 1 choose k. So it can, so the probability is a binomial. As you can see, this is called a binomial distribution. So this is a nice binomial distribution which comes for k heads, which gives you k edges, and n minus 1 minus k tails. Now, if you put p to be lambda by n, you can, this is a very easy exercise I recommend for everybody. Just expand the factorials using Stirling's formula. You get a nice expression which is called the Poisson here. So it has a nice expression in the sense that e power minus lambda, lambda power k by k factorial. So all these binomials will converge to a Poisson distribution. Now, if you calculate the expectation of this binomial random variable, this is not very hard. You can show that this is n minus 1 into p. Now, say p is fixed. Why am I taking p to be lambda by n always? I can take anything else also, maybe p fixed. Say p is half. Say if p is half, you can immediately see the average degree will blow off. In the sense that in your graph, all the degrees will be huge. So every vertex will have huge amount of edges which are coming out, and you don't desire that. And you don't desire that. So what is the technical thing? We assume, generally people assume that p is lambda by n, and the expected degree is converging to lambda. So this I showed you. Now, depending on this lambda, there are different kind of behaviors of the graph. For example, this is from the same website I did the simulation. So this is with lambda is equal to 0.95. You can see there are very few edges in this. If I increase this lambda over 1 now, there are more edges which are coming now. So it's a bit more getting clustered in the sense that there are more things. When lambda is equal to 1, you cannot say even that it's very sparse or very dense. So all these three regimes, lambda less than 1, which we saw here, then lambda more than 1, which we saw here, and lambda equal to 1, can be incorporated in this nice fact about random graphs of the Erdős-Rényi random graph. So what happens when p is lambda, p is equal to lambda by n. So my coin tossing probability is lambda by n, and lambda is less than 1. So if I look at the connected components of the graph, in the sense that if I look at the largest cluster in the graph, it is of the order of log n. So it's quite small when lambda is less than 1. When lambda is more than 1, the largest component is of the order of the number of vertices in the graph. So it's huge. It's almost the whole graph is there. So the largest connected component is of the order of O of n. And when lambda is equal to 1, there is an interesting power which comes up. it is of the order of n to the power 2/3. Now, how does one get to these numbers or these things from the graph? So let me for 2-3 minutes go to a different model, and then I'll tell you how one gets to these numbers. So let me show you a growth process. Suppose I start with origin, which is where I have one particle at a moment. Suppose this particle has some power to split open, and it splits into two particles now. And now these two particles split into one. This lower particle splits into, say, three particles, and the upper particle splits into one particle. Now this is not spreading in exact order. So for example, so what we call this to be the root, the starting origin, and then the root has two children. The lower children has again three children, and the upper one has one children. Now this goes on. So we are producing, so each of these children are again producing. And finally, like say, this goes on like this. So what we are seeing here is a tree. So if I rotate this picture, now this looks like tree. And this is a very nice name. Two biologists and statistician and mathematician coined this tree. It's called the Galton-Watson tree. So what does it do? In the 0th generation, you start off with a root. Then in the first generation, you have three children. So I'm putting x1 is equal to 3. Then in the next generation, so you have 5 children. So x2, 2 is the second generation. Then 3, like this, it goes on. So xn is the number of children in the nth generation. Now some facts about Galton-Watson tree. I'll come because this you are hearing in a technical, non-technical way nowadays in newspapers, but you don't realize you see it as a Galton-Watson tree. So if the average number of children, so this is the number of children, you can calculate the average number of children, is less than or equal to 1, then this tree will be finite, in the sense that this tree will at some point stop growing. It will close down. If this average children is more than 1, the tree is infinite. Now recall something you have been hearing nowadays in newspapers if you are reading about this coronavirus. That is called the reproduction number R0. R0 is precisely this number of children it produces. So for example, last day there was an announcement in Spain that the R0 is increasing. It's more than 1. In India, definitely it's more than 1. It's even more than 2 nowadays. So what it means, at an average, this tree is producing more children, more than 2 children, say. So here is the graph of the coronavirus spreading. So this is the exact tree I was trying to show you. This is a Galton-Watson tree. So in this thing. Now, what is the connection? So I'll not go into the connection. I would have loved to, but due to the time constraint, I cannot show you today the connections, but maybe sometime later. But what happens is the largest connected component is of the order of the total progeny. So number of children this tree produces. It might be infinite. It might be infinite, but say it's a finite tree. Say I've cut the tree at some point. Then the largest connected component will exactly be of the size of the total progeny, total size of your tree. So on the one hand, the C1 is in the Erdős-Srény. This TP is the Galton-Watson tree I showed you. And what kind of children this Galton-Watson tree produces? So all these tree children are produced as x1, x2 are through a binomial distribution. We know binomial was coming in Erdős-Srény, so you have to take this x1 to be binomial. Then you can show, in fact, you can show the total progeny when p is less than n is exactly of the order of log n. It's a minimal calculation which is needed, but this thing. Now let me come to the last part of this talk, which is another modern graph. So configuration model is a way to produce random graphs of desired degree distribution. Now, as you can see, in the Eddo-Shreni random graph, we saw the degree distribution is binomial. But some of our experiments, in fact, in the real life modeling, what we saw was that this degree distribution has to be a power law. So probability that dx is equal to k is equal to k power minus tau. So this condition is not being fulfilled by the Eddo-Shreni random graph. Now say how to construct, say I tell you you have to give me a random graph where you have the power law distribution. For example, how do we construct a random graph? One way was Eddo-Shreni. Another, say I specify you what are the degrees. For example, I have say 5 vertices, 1, 2, 3, 4, 5, and I give you a degree sequence in the sense that 2, 4, 2, 3, 1. Firstly, what does this mean, degree sequence? It means the vertex 1 has degree 2, vertex 2 has degree 4, vertex 3 has degree 2, vertex 4 has degree 3, vertex 5 has degree 1. Can you construct a random graph, explicitly random graph with this degree sequence? Let us see. In a more general question, if I give you a power law distribution of the degrees, can you construct a random graph for me? First criteria to construct a random graph. This is a very interesting, easy example which everybody should try to think about today. This is one thing which is very interesting and one should think about it today, that if you look at the total sum of the degrees, so vertex k has degree dk, say. So if you look at all the degrees, if you sum them up, the total degree has to be even. Otherwise, you cannot draw a graph. So for example, in this example, I was saying 2 plus 4 is 6, 6 plus 2 is 8, 8 plus 3 is 11, 12. So it's an even number. I can construct a graph. Why does this happen, that it has to be even? So there is a beautiful thing called the handshake lemma. So it says, you can just read the red part. It says that the total degree of all vertices is equal to twice the number of edges. So here is the example I was saying. So I need a random graph of 2, 4, 2, 3, 1. So say 1, 2, 4. So these are my vertices. What I do is, say for vertex 1, I need degree 2. I draw these red things here, red, which I call the red spikes. My vertex 2 need degree 4. I make 4 spikes. My vertex 3 needs degree 2. Similarly for other vertices. Now what I do is I start with vertex 1, any one of them, this red quantity. And out of the rest red ones, I choose uniformly one. How many are there? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Out of the 11, with probability 1 by 11, I choose any one of them. Say I have chosen 5. Then I connect this with this. So I have an edge. Then I go to the next one. Then again from the remaining ones, I choose one uniformly. Just it can be anything. I choose one of them. And thus I go on. And this is possible because I am in a even structure. Let me again minimize you and again go to the say I have number of vertices 3 and my maximal degree, so minimal degree is 0, that means I am allowing isolated points, and maximal degree is 5, and or let's make it 6 perhaps. So thus you can see, so what is it doing? It is making all these stubs, and the computer is now uniformly choosing all these points, as you can see. So it's making a configuration model for me with my desired degree distribution. 130 graphs. It's making a complex network. So let's see how this network looks like.
Roger.
Here it is.
Hello.
Hello.
You have only 2 minutes time because.
Okay, fine. I'm finishing. Yeah. Okay. So this is the configuration model you can see. Okay. Now going back to the last part, which is, so what is this importance about this configuration model? Now in this configuration model, what I showed you has a very nice property. So say suppose I construct this configuration model out of the power law degree distribution, and my tau remember that the d1x is equal to k power minus tau. Say tau is greater than 3. Now what I'm doing is I'm picking 2 points in my graph. It can be any 2 points, and I'm calculating the distance between these 2 points, and I'm saying they are hn. This hn is like log n. And interestingly is this regime tau between 2 and 3. In this, the distance between any 2 points is log n. Now, if say you have a million vertices, n is 10 to the power 6. What is hn? Hn is exactly 5.2, which is the 6 degrees of freedom. So this result exactly gives you that you have 6 degrees of freedom in this model. And if tau is less than in between 1 and 2, this is the thing. Okay, I think I have run out of time. So I would like to stop here. Yeah, maybe I'll stop sharing the question. Stop sharing, then I can see the questions if there are any.
To Professor Rajat Rubro Hazra for delivering a nice lecture on network system, including graph theory and statistics also. It is very initiative lectures. So we have a question answer session. So I will go to the question answer right now. To the shortage of time, so I cannot invite all the question, but I will try to take short some question.
Professor Ganguly, could you speak a bit louder? We cannot hear you.
Okay. Chat with everyone, it is not. Yes, sir, it is really helpful. Thank you, sir. Sir, your graph does not there.
Okay, I can see the question if there. So there is a question. So there is a question says that ER graph does there is there a condition? Is there a condition for distance between 2 points?
How do you know what will be the degrees in the random graph?
No, no, it's a, so in the configuration model, what happens is, so you perform an experiment. You have, say, you are looking at a Facebook or a social network. You roughly know how does the degree distribution looks like empirically. Now the idea is to mathematically construct it. This idea was first propagated by Molly and Reed to computer scientists who came up with constructing a random graph with the exact empirical degree distribution which is observed. And then you do the mathematics. Now it happens. So one thing I want to point out that this is only for a fixed graph, that your n is sort of fixed. But nowadays the graphs keep on growing. For example, this coronavirus graph or this other kind of graphs, they keep on growing. And I didn't talk about in the growing graph situation. But these are just from empirical evidences you get this degree distribution. Somebody asked us question that ER graph does the condition for the distance between does there a condition between distance between 2 points? In the ER graph, the distance between 2 points is of the order of log n. So you don't get the so say if your n is 10 to the power 6, you don't get exactly the 6 degrees of freedom. It's not very small. What you need is very small. That's why ER graphs, the distances are not nice, but it's mathematically very important question that how does the distance look like? And there is another question. What will be the degrees in random graph? When we'll get small pxy, like, so there can be any kind of pxy's. Pxy is just the probability. So the probabilities can be very small. For example, I said that so if I look at a random graph in Facebook, there is very, very less probability that I'm friend with Amitabh Bachchan, say. So these probabilities are very small, which are assigned there. Or what are the software programs that you have used for the simulation? Oh, there is a beautiful page in Netherlands called the Network Pages. You can go there. It has beautiful simulations, online simulations you can do. You just need to type in there what are your parameters are, and they produce you wonderful graphs. And this can be done also in R and there are lots of other things. Sir, can we say about the concept of super spreader on COVID? No, okay, that's a completely different question. I guess I didn't speak about spreading of epidemics on random graphs, but definitely degrees with very high, so people with lots of connections. For example, say you look at a politician who is meeting every other people every day, big meetings or going anywhere. They can be super spreader because they're meeting lots of people. So that means the degree distribution is huge. So that's the role of hub, which can be thought of here. No, we toss a coin with probability not exactly equal to half always. It's a fair coin when we toss a coin with probability half, but we are assuming that we can toss a coin with probability p. So half means that there is equal chance of having a head and equal chance of having a tail. But generally, you can just have head with probability p and tail with probability 1 minus p. So the coin is not fair in that sense. So if p is not half. So, but I said fair in the sense that both sides are not tail. So, Drawer, is there a definite way to proceed, like trial and error? No, there is no trial and error. So, can you say that how can we draw a random graph when points and degrees are given? I showed you a way. Just take your degrees, draw those stubs, and from one stub, you start uniformly choosing one other stub. And so I can so those who are interested, just let me share once briefly the website and then I'll be closing. So this is called the, if you can see, this is called the www.networkpages.nl. If you go to networkpages.nl, then you can find a lot of simulations like this, which you can play around and do these things.
Okay, thanks.
Okay.
Rajat. So,
Yeah.
thanks again to Rajat for delivering a nice lecture and answer the question which I asked for the audience. So thanks again. Next, we have a next speaker. The time is right now. Okay. Our next speaker, Professor Ritobhoto Munshi, I think he joined the session. Hello, Indoni? Hello, Indoni? Hello?
Yes, sir. Please go on. Yes, sir.
Yeah, I think Ritobhoto Munshi has joined the session, right?
Yes.
Yeah. Now we announce the name of Professor Ritobhoto Munshi. Okay, everything okay. So I think Ritobhoto Munshi is ready to present his talk. Professor Munshi, are you ready or will it take some time? You will. I will start the session, Professor Munshi. Hello. Hello.
Professor Munshi, are you with us?
I saw the picture. Hello. Professor Munshi, I will announce your name.
Professor Munshi, we cannot hear you. I think your microphone is not working properly. Can you reinsert your earphone again and try?
Yeah, his microphone is not properly working.
We cannot hear you still. I think there is something wrong with the audio connection from your side. Is your mic on?
Should I give a call to Ritubhadra Munshi? Okay. At a call call. Should I give a call? Indoni?
And yes, sir, you can give him a call.
Ah, right. I think some problem.
We are facing some technical issues right now. Please stay with us. Professor Ritubhadra Munshi will continue shortly. Please do not leave the meeting. Thank you for your cooperation. Please stay with us. Dr. Ritubhadra Munshi will join us shortly. Thank you for your cooperation.
Uh,
Sir, I'm calling you. Sir, I'm calling you personally, okay? I'm calling you personally.
out of the
Hello, Dr. Munshi, can you hear me?
Yeah, can you hear me now?
Yes, we can hear you. Thank you for joining us.
Okay, good.
so we have next speaker, Professor of StatMat division of ISI Calcutta, and before the ISI he was in TIFR Mumbai. He's a full professor there, and he received Bhatnagar Award for his great contribution of his research work. And we know that Professor Andrew is a great mathematician. I think Professor Ritubhata Munshi did his PhD under Andrew Will. Is it so, Professor Munshi?
Yeah, that's right.
Ah.
My professor was emphasized.
Okay, so you can start. So your talk is transcendental
Okay.
number, very interesting one. Okay.
Thank you. Thank you for the introduction. It's always a pleasure to present something in colleges in Calcutta. So I'm going to talk about transcendental number theory. So let me start sharing my presentation.
Yes, sir, we can see your presentation.
So shall I go full screen? Will it work?
Yes, sir, sure.
It's better? Okay, great. Okay, so I'm going to talk about transcendental number theory. And so before I start, let me just clarify that this is not really my area of research. So I'm not really an expert, but it's something very interesting. And I think that young people like the students in your college will be very interested in transcendental number theory. So let me start with a quote by Kronecker. So Kronecker was a 19th century number theorist. He worked in algebraic number theory. He said that God made the integers and man made the rest. So by man, of course, he meant both man and woman. So it's, yeah, so we all know what integers are, right? And now from integers, we can produce other types of numbers. And so let's see what, let's go back like a few thousand years, and let's look at a number called pi. Okay, so yeah, so the definition of pi is given by this. So if you take a circle of radius r, and then the area of inside the circle is a constant times r square. So r is the radius, and this constant is called pi. Okay? And that was the definition of pi. And around 2000, 3000 years BC, it was a problem to find out what the value of pi should be. Okay? So at that time, people were not aware of anything beyond fractions and integers. Okay, but in a Babylonian tablet, which dates from 1900 to 1680 BC, there are computations which shows that they took pi to be approximately equal to 3.125. Okay, and at the same time, there is a Egyptian papyrus which says that pi is approximately like 3.1605. And so there was no real formula for pi. What they were trying to do was trying to find out the area of the circle for different values of radius, trying to find out an approximation for that number. And then Archimedes, he was a great Greek mathematician and lived between 287 and 212 BC. And he realized that this number pi should be between 3 plus 1/7 and 3 plus 10 by 71. Okay, so the pi is between 3.1428, that's an upper bound, and 3.1408, which is the lower bound. Okay, and the way he got these two numbers, the upper and lower bound, was his method was this: that you take a circle, say of radius r, and you inscribe regular polygon inside and outside the circle, and then the area inside the inner polygon is less than equal to the area of the circle, and it's less than equal to the area of the outer polygon. Okay, so in this way, by count pi, and then you can increase the number of sides in the regular polygon you're inscribing, and more the sides, and better the approximation that you get towards pi. And this is the picture of Archimedes. Okay, so pi also appeared in India around the same time, may not be as old as the Babylons, but there is a mention of pi in Shulba Sutra, which is like 800 to 500 BC, and where pi is approximated by 28 by 5, which is 3.125. Okay, and Arjavata in 476 AD gave the value of pi to be approximately equal to 3.1416. Okay, and then Madhava between 1340 and 1425 AD. So Madhava was the father which made a lot of contribution to mathematics. He gave two different expressions for pi. So this is the first time where you see an infinite series equated to pi. So pi by 4, he said, is equal to this alternating series, 1 minus 1/3 plus 1/5 minus 1/7, etc. The problem of this series is that it's very slowly converging. So you have to take a lot of terms in this series to get a good approximation for pi. And so he was between 1340 and 1425 AD. And the same thing was rediscovered more than 250 years later by Gregory and Leibniz. And now the series is named after Gregory and Leibniz. Right? So, and also Madhava with another expression where pi is equal to square root of 12 times 1 3 times 3 plus 1 by 5 times 3 square minus 1 by 7 times 3 cube plus etc. And this is much better than the previous one because this converges quite rapidly and it gives quite a good approximation for pi. Right? And so if you're interested to know more about pi, so pi is actually equal to 3.14. This is a decimal expansion of pi. And now we know a way of writing down as many decimal points, as many decimal places as you want. So the computers are there. But back in their time, there were no computers, and these are the only things they could use. And I think by using Madhava's second expression, you can get like 4 or 5 digits of pi accurately. Okay, so the point is that so there was this number pi which came out from geometry, which is as such related to integers. So the thing is that you start with say a circle whose radius is 1 unit, then the area inside the circle would be equal to pi. And right, that's the definition of pi. But pi didn't turn out to be an integer, and people were kind of surprised to see what, and they tried very hard to find out an expression for pi. Okay, so this incidentally is a sculpture of Aryabhatta, who is one of the greatest mathematicians born in India. And this is a page from Shulva Sutra. Okay, and here you can see the Pythagorean triangle or right-angled triangles. I'm not really an expert in this, but there is something which says about right-angled triangle here. Anyway, so now after the invention of calculus by Newton and Leibniz, it was possible to write down different expressions for pi. Okay, and we here a couple of expressions for pi, which are given as limit of n tends to infinity. Of the first one is 2 to the power 4n by n square, and this is 2n choose n square. And this is another one, and n factorial square n plus 1 to the power 2n square plus n by twice n to the power 2n square plus 3n plus 1. And then you also can write pi as a continued fraction, and the continued fraction expansion pi is given by this. So 3 plus 1 by 7 plus 1 by 15 plus 1 by 1 plus 1 by 292 plus 1 by 1 plus etc. So there is no apparent pattern in the numbers, the integers that appear in the continued fraction expansion of pi. It's 3 followed by 7, then 15, then 1, then 292, then 1. There's no real pattern in this expression. But if you look at 4 by pi, and if you write down the continued fraction expansion of that, that has a very nice, it's not a simple continued fraction. You are allowing, here you are allowing only 1 in the numerator. You're allowing other numbers other than 1. Okay, so, but it's quite nice. It has a pattern. So it's 1 square by 2 plus 3 square by 2 plus 5 square by 2 plus 7 square. So you're only getting the odd integer squares in the numerator. And here it's always 2. Okay, so so that the pattern that arises. So if you write down the the decimal expansion of pi that I wrote down here, there is no apparent pattern. It's like, it looks like all the digits are appearing at random over here. If you write down a continued fraction expansion here, also there is, in a different way, some sort of pattern emerges. Okay, so that's a kind of thing that happens in mathematics, that if you're studying an object, here it was pi. If you're studying an object, maybe in when you look at it from different point of views, and from most point of views, you will not find any pattern, but from a particular point of view, some pattern may emerge. Okay, so that's when you know that you're getting near something. Okay, so something which was related to pi was a problem that was posed by the ancient Greeks, which is about squaring the circle. So the problem is this, that suppose you start with a circle and whose sorry, so the radius should be 1 over here, not 1/2. So suppose you start with a circle of radius 1, then the area inside the circle is pi. That's really the definition. And now you want to construct a square whose area is equal to the area of the circle. So the area of this square should be pi. That means the length of the sides of the square should be root pi. Okay? And the ancient Greeks were interested in constructing such a square, but the constraint was that you can only use ruler and compass. So ruler means the straight edge, and the compass is the thing, the geometry, basically the geometry box that you use when you were in school. Okay? So the question was, can one construct root pi using ruler and compass? Okay. Okay. So from this, so there is something called the constructible numbers. So I'm denoting the set of constructible numbers by this notation, script C is a subset of R. So I'm quite number to be constructible if it can be constructed by a ruler and compass starting from 0 and 1. Okay, so let's see what I mean. So for example, so I take 2 points on the plane and I join them by a ruler, and I call this the unit length. Right? And now I am interested in finding out what are the numbers that I can construct, or what are the lengths of line segments that I construct. For example, I can put my compass over here and draw a circle. And also I can put my compass over here and draw another circle and find the points of intersection of these 2 circles. So these 2 circles will intersect in 2 points. So this is 1 point and this is another point. And then if I join them, then we know that that will dissect or bisect this line segment in 2 parts. Okay. So, yeah, so 2. This. See my screen, right? Yeah. So, right. So the point was that from using the ruler and compass, you can construct the length 1/2 over here, and now you can, from here you can see that actually you can construct any integer and also any rational number. Okay, what are rational numbers? Those are the numbers which you can write as an integer by an integer, and in the denominator you are only taking positive integers. Okay? You can also take a and b to be co-prime. So a is any integer, b is a positive integer, a and b are co-prime. These are the rational numbers, and all the rational numbers are constructible. What else can you construct with a straight edge? So here is so I have this line I have constructed. So this is the 2 points that I started with. And now I have constructed length 2, length 3, etc. And I have also marked -1, -2, etc. And now using 0, 2, I can draw a perpendicular on the line segment and passing through 1, right? Using the construction that I gave in the previous slide. And then if I drop the perpendicular, and then on this perpendicular, I can take a unit length, say this is the unit length, and then I can draw the hypotenuse, right? So this will give us a right angle triangle. And now by Pythagoras theorem, we know the length of this line segment, the hypotenuse, is square root of the square of the length of the other two sides. And so that turns out to be square root of 2. Okay. So using straight edge and compass, now I'm able to construct square root of 2. And the square root 2 is not rational. Of course, all of us know about this. So if you want to get a proof that why it's not rational, so suppose it's rational, so square root of 2 is p by q. The GCD of p by q is 1. That means q times root t is p. Take the squares, you get that 2 divides, so sorry, it's q squared t equals 2 equals to p squared. So that will imply that 2 divides p. And since p, so p is even, so you can write p as 2 times r. And now if I plug that in place of p, it turns out that q squared is 2r squared. So that means q is also even. So both p and q have to be even, but we started with pq, which are co-prime. So that's a contradiction. So root 2 is not a rational number. So here we have constructed a line segment whose length is not a rational number. So root 2 is constructible, but it's not a rational number. Okay? So in fact, root 2 is an example of what's called an algebraic number. Okay, because root 2 is a solution of the equation -2 equals 0. Okay, so the nice thing about this equation is this polynomial x squared minus 2 is that the coefficients are integer. The coefficient of x squared is 1, the coefficient of x is 0, the coefficient of 1 is -2. So root 2 satisfies a polynomial equation with integer coefficients, and that's the definition of an algebraic number. Okay, so here a complex number alpha is algebraic. If it is so instead of rational coefficient, you can take integer coefficient because you can clear the denominator. Okay, so the examples, these examples are square root of 2, square root of 3, cube root of 2. These are all algebraic numbers. And now we know that root 2 is constructible. But if you look at cube root of 2, that is not constructible. Okay, so that's not that easy. Okay, but Galois came up with a very clean theory to explain this phenomenon. So he observed that if you have a constructible number, say alpha, suppose it's a real constructible number, right? Then one can find a sequence of real numbers, alpha 1, alpha 2, etc., alpha n, r, such that you can form this tower of field extension. So this is Q is the field of rational numbers. And to that you include now alpha 1. So here in Q alpha 1, you have all the polynomials with alpha 1 and rational coefficient. And now, sorry, this will be Q alpha 1, alpha 2, sorry. So this is the field which is generated by the first two numbers alpha and alpha 2 over Q. And then you have Q alpha 1, alpha 2, alpha 3, etc. Q alpha 1, alpha 2, alpha n. So you get a tower. So if you start with the constructible number, then you can get a sequence such that you get a tower of field extension such that the alpha is in this field. And what can you say about alpha 1, alpha 2, etc.? Is that alpha 1 is a square root of a number in Q. So it's alpha 1 is like square root of 2 or square root of 3, etc. Alpha 2 is a square root of a number in Q alpha 1. So from what is this? Right, so yeah, maybe, I don't know how to do it. So yeah, so here is Q, and then so alpha 1 is the square root of a number in Q, and alpha 2 is the square root of a number in Q alpha 1. And alpha 3 will be a square root of a number in the field Q alpha 1, alpha 2, etc. And alpha n will be square root of a number in this field, which is one less than this. Okay, so so at each point when you're going to a bigger field, you are just taking a square number from the smaller field, from the base field. Okay, and if you can put alpha in such a field, then that alpha will be constructible. And this is an if and only if statement. And so that's what Galois proved. Okay? And oh, sorry, I'll do that to the next page. So here is the picture of Galois who proved this interesting theorem. So this is Galois was responsible for the development of the field theory. Galois died at the age of 20, I think. But his contribution to mathematics is paramount. Okay, now let's go back to the question that we're interested in. So, is square root of alpha constructible, right? So, to answer this, let's observe that when you wrote down the tower of numbers, alpha 1, alpha 2, etc., we know that alpha 1 is algebraic because alpha 1 is a square root of a rational number. Now, I claim that alpha 2 is also algebraic. Okay? Why is that? Because alpha 2 square will be a number in the field generated by Q alpha 1. And so it can be written as A plus B alpha 1, right? Because any number, any element in Q alpha 1 is a polynomial in alpha 1 with rational coefficients. But the higher powers of alpha 1 can be written in terms of alpha 1, right? Because alpha 1 square is a rational number. Alpha 1 cube will be a rational number times alpha 1, right? So we have this alpha 2 square equals to A plus B alpha 1. And so now I do this elementary algebra. And take the square, right? Because alpha 1 square is a rational. Now B square is also rational. So this thing becomes irrational. So alpha 2 square satisfies this quartic equation, the degree 4 equation. Alpha 2 to the power 4 minus twice A alpha 2 square. Twice A is a rational number plus this, which is also a rational number, equals to 0. Okay, so not only alpha 1 algebraic, alpha 2 is also algebraic. And if you repeat the same thing, you can show that alpha 3 is algebraic, alpha 4 is algebraic, etc. Alpha n is also algebraic. So all the number that was appearing, that were appearing in the tower are all algebraic. Okay, and there is this fact that the sum of two algebraic number is algebraic, and the product of two algebraic numbers is algebraic. Okay, so anything which can be written as a polynomial in alpha 1, alpha 2, such as alpha n, has to be algebraic. Okay, so in particular, the that it started with alpha has to be algebraic. Okay, so now from Galois theorem, what we have proved that any constructible number is algebraic. So now you can ask whether root pi, if it is constructible, it has to be algebraic. So is it algebraic? Okay, so now let's introduce this notation. So Q bar is will denote the of algebraic numbers in the field C. Okay, so it's all complex numbers which satisfy some polynomial equation with rational coefficient. Okay? And now we are interested in finding out whether root pi is algebraic, and that same thing as asking whether pi is algebraic or not, because if root pi is algebraic, its square has to be algebraic, and if pi is algebraic, its square root also has to be algebraic, right? So, so now we are interested in finding pi algebraic. Oh, but maybe all complex numbers are algebraic. We haven't ruled it out yet, right? So let's see whether there is a complex number which is not algebraic. And this was proved by Liouville around 1844. Okay, so what he showed is the following. So suppose alpha is an algebraic number of degree larger than 1. Then there exists a constant which depends on alpha only, and such that alpha, the difference between alpha and any rational number p by q is at least c by q to the power n. Okay, So if you take any rational number p by q and find out the distance between alpha and p by q, it has to be at least c by q to the power n. So how do you prove this? Okay, that's quite simple. So suppose alpha is a number. If it's complex, then you have to just break it into two parts. Okay, so suppose, all right, yeah, probably. Yeah, I should probably just start with alpha, which is real algebraic over here, and not complex algebra, because I'm talking about distance from the rational numbers, real rational numbers, not the algebraic, not the complex rational numbers. So yeah, sorry. So we should have here q bar intersection r. Okay. So suppose alpha is in q bar intersection r, and suppose p is the minimal polynomial satisfied by r alpha, right? So alpha is an algebraic number, so it will satisfy some polynomial equation with integer coefficient. So I'm calling p to be such a and p to be the minimal such polynomial, so smallest degree polynomial. Okay. Then by mean value calculus, we know that the value of this polynomial at alpha minus the value of the polynomial at p by q is equal to the distance between alpha and p by q times the derivative of the polynomial at some point between alpha and p by q. That's a first mean value theorem, right? And now, since alpha satisfies the polynomial, so p alpha has to be 0. So this guy is 0. And since this is the since p is irreducible, it cannot have a rational number as a solution. Because if it has a rational number as a solution, then you can actually factorize it over the rational. So p by q is not 0. So the polynomial is not vanishing at the rational number. Then if you multiply this by q to the power n, then it will be, because it's of degree n, then all the denominators will be cleared. The coefficients were already integer. And so to the power n ppq is an integer which is not 0. Okay. So that means that this is at least, if you take the absolute value, it's at least 1. So the size of this value p by q is at least 1 by q to the power n, right? Okay, so now what we have seen, so we know that this is 0, and this number over here is at least of size 1 by q to the power n. So this distance is 1 by q to the power n divided by p prime xi. Now, what can you say about p prime xi? Okay, so here. So now suppose alpha and p by q is the distance less than or equal to 1. Then the absolute value of p prime xi, because xi is between alpha and p by q, using calculus, you can show that this only depends upon the alpha, because the polynomial p depended only on alpha and not the rational number. And now you are only looking at a unit length around alpha, so the value of the derivative of the polynomial in that interval will only depend upon alpha, not p by q. Okay? So it's some constant which depends on alpha. So you get that alpha minus p by q times p prime xi is greater than or equal to 1 by q to the power n, and p prime xi is less than c alpha. So this distance is 1 by q to the power n c alpha, and so the small c alpha to be 1 by capital C alpha, and you get this. So that's Liouville's theorem, that if take any rational number, the distance has to be at least some constant by q to the power n. Cannot be approximated better than that. Okay. As a corollary to this, Liouville showed the existence of transcendental numbers. Transcendental numbers means numbers which are not algebraic. So here's the corollary. So if you look at number, so 1 by 2 to the power 1 factorial plus 1 by 2 to the power 2 factorial plus 1 by 2 to the power 3 factorial, etc., then this is not going to be an algebraic number. Okay. So how do you prove that? So you take two rational numbers, pk and qk. So these are integers, pk and qk. So pk is, you take the first k terms in this series and multiply it by 2 to the power k factorial. And you see that it becomes an integer, because 2 to the power k factorial by 2 to the power j factorial for j less than or equal to k is an integer. So this is an integer, and qk, which is 2 to the power k factorial, is also an integer. So now let me find out the distance between theta and this rational number pk by qk. And pk by qk is just this. So first k terms in the series of theta. So this distance is the tail. Okay, and you can very easily show that the tail is bounded by this, and which is qk power k, right? So now this k is independent of the degree of theta. So suppose theta is algebraic of degree n, then by Liouville's theorem there will be a c such that this distance cannot be less than c by qk to the power n. But if I take k very large, then I can make 1 by qk to the power k to be less than c by qk to the power n, right? Because c and n are only depending on theta, and k I can take to be as large as I wish. So this will contradict Liouville's theorem. That will mean that this is not really, theta is not really an algebraic number. So Liouville was the first person to prove that there are numbers, complex numbers, or actually real numbers, which cannot be a solution of algebraic equation. Okay, so this is picture of Liouville. But then came Cantor, and who proved this. He not only proved the existence of transcendental number, he proved that almost all numbers are transcendental. Okay, so what did Cantor show? So Cantor showed that the set of algebraic numbers, q bar, is in fact countable. So you can actually get a one-to-one correspondence between the set of algebraic numbers and the set of natural numbers. Whereas the set of real numbers and the set of complex numbers are not countable. And they cannot be put in one-to-one correspondence with integers or natural numbers. And so from there, it follows there are infinitely many, and in fact, uncountably many real or complex numbers which are not algebraic. Okay. Okay, so what will be the quick way of proving that q bar is countable? All right, so here you're only putting solution of polynomial equation of integer coefficients. So now how many polynomials are there of degree n with integer coefficients? There are only countably many. So there are only countably many algebraic numbers of any given degree, and if you take the union of all those, you get all the algebraic numbers. And countable union of countable sets is countable. So that proves that the set of algebraic number is countable. Okay. Okay, here is the definition now. So any complex number which is not in this algebraic closure, a q bar which is not an algebraic number, is called a transcendental number. So Cantor showed that almost all numbers are transcendental. And then Liebeck came, and Liebeck showed that, in fact, if you take the measure of the set of algebraic number, it is of measure 0. So if you pick any real number randomly, in whatever sense, as long as you have a nice non-discrete measure or something on the real numbers, it's almost surely transcendental. Okay? But still, it doesn't say anything about that particular number pi that we have been interested in for the last 3,000 years. Okay, so but before going to pi, let me take a short detour and say something about something very simple, something about, say, square root of 2, which is quite simple, right? So we know that it's not a rational number, it's an algebraic number. And also, if we write down the decimal expansion, it looks like this. These are the numbers. Again, there is no apparent pattern in the decimal expansion of square root of 2. And the square root of 2 also intrigued the ancient Greeks, the Babylonians, and Indians. And in fact, if you the Sutra, which is again from 800 to 500 BC, there are indications that they thought that root 2 is not rational, because they had several different ways of approximating root 2 by different rational numbers, but it's not really stated stated precisely that it's not rational. Okay, So the first such theorem came from Theodorus, who on 370 BC proved that the square root of 3, square root of 5, and the square root of 17 are not rational numbers. Okay, and they can actually do it in a few lines, as we showed, like square root of 2 is not rational. The same thing. That was his proof. Okay, and then Borel conjectured, and so this is a very nice conjecture about numbers like square root of 2. So he said that if you take say algebraic real number, so I should take q bar intersection r over here, which is not a rational number, and then I take an expansion of this number with respect to certain basis, say base b. Okay, so this b, capital B, is an integer plus 0.b1, b2, b3, etc. These are the digits in the b array expansion of alpha. So these bi's are between 0 and b minus 1. Right? If you take b to be 10, then this is the usual decimal expansion. So Borel conjectured, then all the digits, so any number between 0 and b minus 1, should occur in this expansion at least once. And actually, if it occurs at least once, you can show that it occurs infinitely often. Okay? So Borel's conjecture is it's equivalent to showing that any digit should occur infinitely often in the B array expansion. So if you take the square root of 2, for example, and take the decimal expansion of square root of 2, it is expected that all the digits should appear infinitely often in the decimal expansion. Okay, but that's not really known, right? So what we know is that the decimal expansion of square root of 2 is not periodic. That's quite easy, because if it's periodic, then you can get it to be rational. And we know, the best thing that we know is that among the digits between 0 and 9, at least 2 of them occur infinitely often in the expansion. Okay, so yeah, that's kind of triviality. It just says that if we had that only one would appear infinitely often, the will only consist of that, and that will give you something. So beyond this triviality, we do not know anything about the decimal expansion of square root of 2. Again, if you write square root of 2 in continued fraction, there is a very nice pattern. Okay, so it is just 1 plus 1 by 2 plus 1 by 2 plus 1 by 2 plus s squared. Okay? So it's a periodic continued fraction. In fact, there is a theorem in the continued fraction theory which says that if you have a periodic continued fraction, then the number which is represented by the periodic continued fraction is a quadratic irrational. It's an even all leaves statement. Okay, and then in 17th century, another interesting number appeared in the arena. This was given by Jacob Bernoulli. He was probably working on probability, I think. And he was interested in finding out this limit, a limit 1 plus 1 by n to the power n. Okay, and he knew that it's converging, and it should be converging to a certain number. He didn't denote it by e. In fact, Leibniz denoted it by b. I think b for Bernoulli. But like 40 years later, Euler kind of changed it, and he named it e. I don't know whether e was for Euler. And yeah, and from that time onwards, it's still denoted by e. So e is the limit of this, and is the natural base logarithm, and it's also given by this series. So it's 1 plus 1 by factorial plus 1 by 2 factorial, etc. And this is as the decimal expansion. Again, there is no apparent pattern in the decimal expansion from e. But this e is almost like pi in the sense that whatever we know about e is whatever we know about pi. Is more or less easier than pi. Okay? And in fact, there is a very interesting relation between e and pi due to Euler. He showed that e to the power pi I is minus 1. Right? Okay, we'll come back to that later. Okay, so Fourier in 1815 actually showed that e is not a rational number. We'll see the proof shortly. And Hermite proved in 1873 that E is not an algebraic number. So it's a transcendental number. And okay, so this was the first case, I think, where someone proved a number which comes from analysis to be transcendental. Okay, so this is the picture of Hermite to prove that E is irrational. Okay, so this is the proof of irrationality of E. So it's enough to prove that 1 by E is irrational. Okay, and if you look at 1 by E, then you have an alternating series expansion of e to the power minus 1, right? It's 1 minus 1 by 1 factorial plus 1 by 2 factorial minus 1 by 3 factorial. It's the same thing as here, but with alternating positive and negative signs. Okay, now suppose you take an capital N to be an odd number and truncate the series expansion, and then you can get a lower bound and upper bound for 1 by E. Okay, so this part gives you a lower bound, and this part where you are adding an extra 1 by n plus 1 factorial gives you an upper bound. And so you get that 1 by E is between an by n to the power factorial and an by n to the power factorial plus 1 by this, right? So this I'm just, yeah, the denominator is n factorial. The numerator will be some integer. So I'm calling it Z. And so it follows from here that, oh, sorry. So here you should have E inverse, okay? So n factorial times E inverse is n and 1. But now an is an integer. Yeah, so an is an integer, and so it is between these two, and so there cannot be any integer between these two. These are two consecutive integers, and there cannot be a consecutive a number between these two. So it shows that 1 by E times n factorial is not an integer, and that means E cannot be a rational number, because if E had been a rational number, then you can just take, so if E is like P by Q, then you can take Q factorial in place of n factorial, or Q plus 1 factorial in place of n factorial, depending upon, depending upon its order even. Yeah. So that's the proof of irrationality of E was due to Hermite. Okay, and so let me just give indication of how to prove the irrationality of pi. This is something a little more difficult than irrationality of E. So suppose pi is a rational number, so pi is a by b, and then you define this polynomial x to the power n minus a minus bx to the power n by n factorial. Okay, and now you define another polynomial which we call capital Fx, which is taking small fx minus the second derivative of small fx plus the fourth derivative of small fx, etc. Okay. All right. So now you observe that if you multiply this polynomial fx by n factorial, then it will have integral coefficients. And not only that, if you take the derivatives, then they also have integral values at the point x equals to 0 and x equals to a by b. Okay? So at these 2 points, 0 and a by b is the pi. These numbers that appear over here, they have integral values. All right. So now start with, so these are things that you can check for yourself. Okay? This is just simple mathematics. Now you start with the derivative of capital F prime x sine x minus capital Fx cos x. And by simple computation, you can show that this is small fx times sine x. Okay? So if you integrate small fx times sine x, then you get back capital F prime x sine x minus Fx cos x. If you do it from 0 to pi, then you get from 0 to pi on this side. And for x between 0 and pi, you get that fx sine x is bounded by pi to the power n, a to the power n by n factorial. So this is coming from the definition over here. Okay, and so this integral, because the integrand is bounded by 0 and this is between 0 and, so there is an extra pi, this pi, and this is strictly smaller than 1. Okay, as if you take n to be sufficiently large. So pi is fixed, And a by b is the, if assuming that pi is a by b, a also is fixed. So this is some power, some fixed number to n, and this is n factorial, and we know that n factorial grows faster than a fixed nth power, nth power of a fixed number. So you can make it smaller than 1 if you take n large enough. And that's a contradiction, because we know that this guy has to be an integer, that it can is between 0 and 1, and there are no integers between 0. So that's the proof of irrationality of pi. Okay, so now let's see the proof of transcendence of E, which is much harder. Okay. All right. So how do you prove the transcendence of E? With this integral 0 to t e to the power t minus x fx dx. Okay, so f to be, just take f for the time being to be any real polynomial of degree n, right? And now by repeated integration by parts, you can show that it is the difference between these two. Okay, you have e to the power t, and you get all the derivatives of f at evaluated at 0, which is the lower boundary point. And here you have all the derivatives of f evaluated at t, which is the upper boundary point. Okay, so that's a relation, and that's a way of writing down this integral in terms of the derivatives of the function f. And also, this it is bounded by, you put the absolute value inside the integrand, and that you can easily bound by this. Okay, so where is absolute value of f is the polynomial that you get by putting out coefficients. Okay, so clearly this is bounded by this. Right. So now my target was to show that E is not algebraic. So suppose, again, it's by contradiction, so suppose E is algebraic, and so it will have satisfy a polynomial equation. So it's a0 plus a1e plus etc. So it's a degree n polynomial equation with integer coefficients. And now from this, I manufacture a polynomial. So the polynomial here, what I'm writing down, will depend upon the degree n, and will depend upon the prime p, which I'm going to take to be quite large. Okay, so I want x to the power p minus 1, x minus 1 to the power p, etc. x minus n to the power p. Okay, so this polynomial has a 0 of order p minus 1 at 0, at of order 1, of order p at 1, order p at 2, order p at n. Okay, and the degree of f is which is 1 times p minus 1, and this number is less than equal to twice np. Okay, so that's the degree of the polynomial. So now I'm interested in this number. Let's call it capital J. Okay, so this a0, a1, etc., n are the integers which were appearing in the assumed polynomial equation satisfied by E. Okay, and so small f is that polynomial that I just defined. And if you can easily check the absolute value of f evaluated at any k, where k is between 0 and n, is bounded by 2n to the power m, which is 2n to the power 2np. Okay, m was the degree of f, and we have seen that m is bounded by 2np. Okay, so if you take the absolute value of j, so that is bounded by a0 times absolute value of I0 plus absolute value of a1 times absolute value of I1, etc. And previously we have for the absolute value of it, bound for that in terms of the absolute value of small f, right? So if I use that and this over here, then I get the absolute value of j is bounded by some constant to the power p. Okay? And this constant doesn't depend on p. It only depends upon the integers a0, a1, etc., an. All right. Alternatively, if you look at j, the j is also, if you go back here, so I have an expression for it in terms of the derivatives of small f here, right? So using that expression, I can write j in terms of the derivatives of the polynomial small f, okay, with integer coefficients. And now I study these values of the derivatives of f at integers k. So if k is between 1 and n, then if you look at the j derivative, so recall that if you take 1 and n, then f has a 0 of order p at that point, right? So that j derivative will be vanishing if j is less than p. But if j is greater than or equal to p, then you'll get some derivative, and this will depend upon fx by x minus k to the power p. It will depend upon the derivative of this polynomial. Okay. So, but these are all integer coefficient polynomial. This is also an integer coefficient, and it's an integer. So it follows the p factorial divides the jth derivative of f evaluated at k. Okay, so all these numbers, if k is between 1 and n, are divisible by p factorial. Now k equals to 0 also appears in this expression. So we have to study what happens at k equals to 0. And in using the similar argument as before, you can show that not p factorial, but yeah, p factorial divides the jth derivative at 0 for p. But p minus 1 factorial divides the p minus 1th derivative of f at 0. But p factorial does not divide this. Okay? And if you use this knowledge about the divisibility of f by p factorial and p minus 1 factorial, we get that the whole thing is divisible by p minus 1 factorial. And so it follows that the absolute value of j should be at least p minus 1 factorial, but it's not 0. Okay, because it's not divisible by p, right? Because there is one term which is not divisible by p. Okay, and it is also less than or equal to c to the power p. And again, as the factorial of p grows faster than the pth power of a constant, it is a contradiction when p is larger. Okay, so that showed that pi is not algebraic. Okay, that was proved by Lindemann. So that was is algebraic, but a similar proof exists which shows that pi is not algebraic, and that was given by Lindemann in 1882. Okay, and that also showed that square root of pi is not algebraic, and so after like 2,000 years or so, he could finally prove that a square cannot square a circle. Okay. All right. So let me introduce another function, which plays a central role in modern mathematics. It's called the Riemann-Zeta function. This was introduced by Euler, but Riemann made a fundamental contribution in this field, and so we have named it after Riemann. So zeta s is given by 1 plus 1 by 2 to the power s plus 1 by 3 to the power s, etc. For real s, so s I'm taking here to be a complex number. If the real part is greater than 1, then it's absolutely converging. Okay. Riemann shows that if you know some nice analytic properties of zeta s, then you can say a lot about the distribution of the prime numbers. Okay, so that was his main contribution. And of course, the famous Riemann hypothesis says that if you can show that non-trivial zeros of zeta s are all on the central line, the real part of s equals to half, then you will have a very nice count about for the number of prime numbers less than or equal to x. Okay? Much better than what Gauss had conjectured. Okay, as I said, that Euler was the first who studied this zeta function. And he first used the divergence of zeta at 1 to prove that there are infinitely many primes. And then he showed that zeta 2 can be evaluated as pi squared by 6, zeta 4 is pi to the power 4 by 90, zeta 6 is pi to the power 6 by 945, and so on. And in fact, he showed that zeta at any even rational multiple of pi to the power 2n. Pi, we have seen, is transcendental. So the transcendental part of zeta 2n is pi to the power 2n times rational number. But what about zeta 3, zeta 5, and zeta 7? What about the zeta at odd integers? Okay, Euler couldn't do it, and we can't do it now. Okay, we don't know whether these guys are transcendental or not. So it's conjectured that these are all transcendental, and they are moreover algebraic independent of each other. So that means if you include in Q zeta 3, then zeta 5 will be transcendental over that field. It's not only transcendental over Q, but transcendental over that field. Okay. Okay. So so that's one problem that was bothering people in 19th century, and also number, which also popped up in a paper of Wheeler, with the limit of 1 plus half plus 1/3 etc. plus 1 by n minus log n, okay, which has the this is called the Wheeler constant, which is this decimal expansion. And this is also related by zeta 1, because this is like the partial sum of zeta 1, and it has a pole at, and you're kind of subtracting the residue and trying to find out the first coefficient in the expansion of zeta around the pole. Okay, and so you're asking whether this is rational, transcendental, rational number, or I think nothing is known about this number gamma. Okay, another source of number is this gamma function. Okay, so if you, this is something that we learned in college, right? And for example, this is an open problem that if you take the gamma function at 1 by 5, is this irrational? Okay. We know that gamma r is transcendental for r value. This is known. This were proved recently, not in 19th century or so. Anyway, as you know, there are quite a few questions about transcendental numbers that bothered people in 19th century. So at the beginning of 20th century, when there was the second International Congress for Mathematicians in Paris, I think, Hilbert came up with a list of, this is a picture of David Hilbert. He came up with a list of 23 problems to be tackled in the 20th century. Okay, and so I found out that curiously this was announced in August 8th in 1900. So today is August 9th. Yes. And in the list of this 23 problem, the number 7 is something interesting. He asked whether e to the power pi and 2 to the power square root of 2 transcendental or not. He made a remark that he thinks that this question is a lot harder than his next problem, which was number 8, and that was concerning the Riemann hypothesis. Okay, but in a twist of history, and Gelfand and Schneider settled Hilbert's 7th problem in 1934, just after 35 years after Hilbert posed the problem. And they actually proved something much more general than what Hilbert was expecting. Okay, so first they proved that alpha to the power beta, if you take an algebraic number and raise it to an algebraic number which is not a rational number, then it is transcendental. So that shows that 2 to the power square root of 2 is transcendental. And they also showed that log alpha 1 by log alpha 2, if alpha 1 and alpha 2 are algebraic numbers, is also transcendental. Okay. And now if I look at e to the power pi, I mentioned Wheeler's equation, e to the power pi I equals to minus. Yes, you can derive that e to the power pi is minus 1 to the power minus I. Of course, you have to make meaning of what is the meaning of raising an integer, negative integer to a complex number. But if you can make sense of this, then e to the power pi is minus 1 to the power minus I. Here, minus 1 and minus I are both algebraic, and minus I is not rational in some sense. So this also follows from the thing that alpha to the power beta is transcendental. So Gelfand and Schneider settled Hilbert's 7th problem completely in 1934. This is a picture of Gelfand. The first one is Gelfand, the second one is Schneider. But the zeta function turned out to be much more difficult, and the Riemann hypothesis is still open. And then in the last 120 years, we haven't made even a iota of progress in this towards Riemann hypothesis. So he was completely wrong that he predicted that transcendental number theory is difficult than the hypothesis. That's not true. Anyway, there's this, I was talking about zeta 3, zeta 5, and zeta 7, etc., the zeta at odd numbers. And it was shown in 1978 that zeta 3 is irrational. Okay? And the proof is almost like the proof that the irrationality of pi. Okay? But it's not known whether zeta 3 by pi to the power 3 is rational. Okay, recall that, you know, if you take zeta 2 by 2 square, it's rational. If you take zeta 4 by pi to the power, zeta 2 by pi to pi square, it's rational. If you take zeta 4 by pi to the power 4, it's rational. Okay, so you can ask whether zeta 3 by pi to the power 3 is rational or not. It's expected to be rational. It's there, but it's not known. Okay, and nothing is known for Zeta 5, Zeta 7, etc. In 2000, it was proved that out of this Zeta 5, Zeta 7, etc., infinitely of them are irrational. Okay? But one cannot pinpoint which are irrational. And it is expected that if you take pi, Zeta 3, Zeta 5, Zeta 7, Zeta 9, Zeta 11, etc., they're all algebraically independent of each other. So they're not only transcendental, Zeta 5 cannot be, Zeta 5 and Zeta 3 cannot satisfy an algebraic relation between each other. So they are transcendental with respect to each other. Okay? So there are a lot of interesting problems about transcendental number theory, and I think one of the most interesting problem is the last thing that I wrote down. Even showing that Zeta 3 is transcendental would be a fantastic achievement. There is no known method of doing that. To find out a new theory to deal with such problems. Okay, so with that, I'll stop. Okay, thank you.
Professor Ganguly?
So it is a very nice talk on transcendental theory. He gave a very brief historical development of the transcendental theory right from the beginning. So, okay, there are some questions about the audience. I see the chat box. Okay.
So I did get the chat box here.
Oh, thank you, sir. Thank you. Is there what will be the motivation to find formula of transcendental formula? Mr. Munshi?
Yeah, what was the question? Yeah.
The one guy has asked the question, what is the most motivation of finding the transcendental formula? I think it is a very trivial.
I don't know what would.
Okay, I skip the question. Yeah. All the transcendental numbers are irrational, but irrational numbers are not transcendental.
That's right.
Is the statement true? Yeah.
Yeah, it's true. Of course, root 2 is irrational but not transcendental.
Yeah. Thank you, sir, for your information. Okay. Is there any other question? No, I don't see so. I have some thanks. Okay. So I have a question. Professor Mun.
Yeah, sure.
You
go ahead.
know that Roth has 59 on the working on transcendental number, and
right.
Hello, Professor Munshi.
Hello. Yeah, I lost you at the end. So you said that Roth's theorem said what?
Roth, here he's the Roth. He said that from the Lewis theorem, proved that the transcendental number are not properly approximated by the rational number. Those are the number transcendental, right?
Right. Lewis theorem says that.
A lot of our you give alpha is a algebraic number minus p by q. We have told is that less than 1 by q to the power n. And another way after that, Cantor proved that almost all numbers, real numbers, are transcendental. Almost in the same respect to the cardinality, right?
It's a cardinality, right? And also with respect to the Lebesgue measure. So if you take the Lebesgue measure,
he proved that but I think that Hilbert was very much focused on the theorem. The numbers of the form a by 2 to the power b, where a not equal to 0, not equal to 1, is a transcendental number. I think Hilbert proved within his 23 problems, he proved the 7th problem. Looking over that matter, a to the power b.
Yeah, that was his 7th problem. Yeah, that if a is not 0 and 1, it's an algebraic number, and to the power b, where b is a algebraic number but not a rational, then it has to be transcendental. Yeah, that was his main goal.
He looked at the problem and he proved the 7th problem of looking after the matter, right?
Yeah.
It's a very nice talk. So tensor number has a wide application in the first order, second order differential equation. I think so.
No. Yeah, it has a lot of application to analytic number theory, like circle method and all that.
Analytic function on differential equations of first order, second order, like that.
Yeah. Okay.
Yeah.
Yeah. Maybe.
A lot of work. It is extensive work has been done on the transcendental number. Thanks for your nice lecture and brief description of the historical definition of transcendental number theory. So I think all the audience enjoy your speech. Thank you once again.
Thank you. Yeah, thank you. So yeah, so there is one question that just saw that Riemann hypothesis proven recently or not? It's not. It has not been proven. Yeah.
Yeah.
Okay. So yeah, it's people announcements. So, but they are always premature. Yeah.
Inonil?
Yes, Professor Ganguly.
Hello.
Yes.
So
yes, Professor Ganguly, I'm here. Yeah. Yes. Thank you, Professor Munshi, for joining us tonight. Thank you for an interesting talk.
Thank you.
I hope you had a great time. We had a great time too. And I must thank all of the audience members for being with us here today. And this is the end of the session. And for those who are asking for the feedback links, please note that we will provide the feedback link tomorrow. And the link shall be sent to your registered email addresses automatically. So I hope all of you join us tomorrow. We will have our second technical session tomorrow, and we all hope to see you there. Thank you for joining us, and thank you for your cooperation today. The time has been mentioned in the schedule PDF. There is a detailed breakup of the schedule, and the timestamps are present in the schedule PDF. I'll still mention it. The technical session number 2 starts at 4 p.m. Same time as today. Okay.
Thanks. This is the end of the session.
Thank you all for joining us. I'm ending the session here.